I'm here with Chris Curry from Iowa State University. Again, my name is Brian Krug from the University of New Hampshire, and we're going to be talking about growing lettuce and culinary herbs hydroponically today. Before we go any further, I do want to make sure that we do thank our sponsor, Hort Americas. They've graciously sponsored this webinar so that we can bring this information to you free and cover some of our costs like this software that we use go to training. So without any further delay, I'm going to unmute Chris Curry, and he can take on the rest of the presentation for a little while. All right, Chris, you should be live and ready to go.
All right. Do you hear me out there?
We do.
All right, excellent. Well, thanks for the introduction, Brian. I appreciate the chance to talk to you a little bit today about growing lettuce and culinary herbs and hydroponic production systems. So I guess we'll start out with just kind of going through why would you want to grow lettuce and herbs? Well, as we all know, we've heard a lot about the increased interest in food produced locally. And really, during the summer, we've got a lot of great farmers markets. We've got a lot of great outdoor production happening. But as I stand up here in Iowa, looking out my office window at the snow-covered ground and somewhere in the maybe teens outside, there's really only one way to get local food in the winter in some locations. That's going to be growing in a greenhouse. And greenhouse food production, there are a lot of different types of crops that you can produce in a greenhouse. Okay, we've got tomatoes, cucumbers, strawberries, peppers, lettuce, and herbs. So there are a number of different crops that you can produce. But one of the big differences with lettuce and herbs is think about what we're harvesting. Think about what that yield is compared to tomatoes, cucumbers, strawberries, and peppers. Think about what those products are. Those are all going to be fruiting crops. Lettuce and herbs are produced for their leaves. All the other crops are produced for their fruits, and as a result, the time to produce a lettuce crop or an herb crop is much shorter compared to fruiting crops. So this means that this short crop time allows for what I call gap production. And I think that this really suits these crops well. As when I say these crops, I'm talking about lettuce and herbs. I think they're well suited for alternative production for fall and maybe that winter crop. So are you looking for something other than poinsettias to grow in an ornamental greenhouse? You know, when you start getting into some of the other vining crops, they're a longer crop time. They have real exacting requirements that you need to provide. And so lettuce and herbs are two short crops that you might be able to fit in and diversify your mix with other ornamental production. So I think that's kind of some of the real opportunities that you have when looking at lettuce and herb production. So what are you going to grow? Well, the stuff that sells. And really, with lettuce, there are three main types of lettuce that we see produced hydroponically. First is going to be butterhead lettuce, and that is by far the most popular. But in addition to butterhead lettuce, there's loose leaf lettuce and romaine head lettuce, and there are also a large number of other greens that can be grown. I was just over at Beaver Creek Farms west of town here, and I was looking at their hydroponically grown mustard, collards, kale, and arugula. So there are other types of greens aside from just lettuce. With herbs can really be split into two groups: annuals and perennials. And when you look at what really sells, the number one herb that is bought in the marketplace is going to be basil. Other annual herbs include dill, cilantro, and flatleaf parsley. The good thing about those crops, again, they're going to be relatively short crop time, and they grow pretty quickly. Other perennial herbs that are also good sellers include rosemary, sage, oregano, chives, and thyme. But with perennial herbs, you have a bit longer crop time. So here's a shot. This is, again, probably it's probably the most popular lettuce crop on the market, and that's butterhead lettuce. And this is likely the cultivar Rex. But, you know, this is a great product to produce hydroponically. It tastes great. Consumers really like it. And then, like I said, for herbs, it's going to be that sweet Italian basil. And so these are some shots from our greenhouse. We were doing some trials with a bunch of different cultivars, and this is just one of the cultivars. But this is, again, the #1 selling herb. So how are we going to grow these crops? Well, starts with propagation. And as we go through the production of lettuce and herbs today, I'd like to underscore that this is really a large topic that could take up many hours, and we're just going to be giving you kind of a view from 30,000 feet from this presentation. So hopefully we're going to be presenting more in-depth seminars in the future, giving you some more details. But with propagation, the majority of these are going to be propagated by seed, all the lettuce and most of the herbs. Although there are some herbs that are going to be propagated by stem tip cutting, such as rosemary, some mints, and other cultivars that you want to propagate genetically. But for seed production, we're basically going to be seeding our crops into one of three types of materials, three different substrates. One is going to be rock wool. Two is going to be phenolic foam. It goes by the trade name Oasis, those Oasis cubes. And the third is going to be a stabilized peat or coconut coir substrate. So this isn't quite necessarily the Performa plugs, although those would work. You can also get peat or coconut coir that's been stabilized by having a mesh wrapping around each individual cell or each individual seedling root ball. So seedlings can be grown either on the bench or in specialized propagation systems. Here, I'd like to call it benchtop, but it's actually tabletop production of seedlings. And you can see we've got our 10 by 20 flats, we've got a sheet of rock wool cubes, and then we've got lettuce sown in those cells. And they're sitting on top of a heat mat to provide heat to that substrate to get rapid germination and uniform germination. Now, there are also more specialized systems for propagating seedlings for hydroponic systems, and this is one of them. This is kind of like a cascading bench. Now, you see, if you look on the left-hand side, you can see the little spaghetti tubes. That's feeding the nutrient solution, and then there's an angle that the nutrient solution flows down, and those seedlings are sub-irrigated, okay? Compare that when we look at back of the bench or tabletop production. These are going to be irrigated by hand or overhead irrigated, whereas these are sub-irrigated. And then that nutrient solution just drains out of the trays and goes back and gets recycled. So those are really the two main ways that you're going to propagate your seedlings. Okay, now you've got seedlings. What are you going to plant them into? Well, there are a number of different hydroponic production systems. We've got Dutch or Beto buckets. We've got coconut slabs, we've got rock wool slabs. Those tend to be geared more towards those vining crops, the cucumbers, the tomatoes, and the peppers. For the production of lettuce and herbs, there are two systems that are really well suited for this. The first is the nutrient film technique, and the second is the deep flow technique. So we'll start with the deep flow technique. There are other names that this will go by, including raft culture, deep flow hydroponics, raceway culture. So it's all kind of the same idea, though, where we've got a large volume of water and we've got a raft floating on top of the solution that the plants are placed into, and those roots then sit in that water. Now, this is a shot of a system up in Saskatoon, Canada, before they were really getting going. And here they've got, they're using boards to build their sides. Then they put down some liner on the bottom to kind of protect from that rough concrete floor in the greenhouse, as well as provide a little bit of insulation. And then they're going to line that with a polyfilm lining, probably 1 or 2 layers. And you can see from the two different sized rafts that they got different spacings. And you can use these different spacings for different crops or for the seedling phase and then the finish phase. Now, one of the reasons that they call this the raft or the raceway system is that we can move plants in this floating solution depending on the size of the bed during production. So if you look at the left-hand side, we've got our plants that were recently planted, okay? And then what happens is as you look to the right, you can see there's plants that are of harvestable size. Now, if you configure your system correctly, you can actually harvest those rafts when the plants are of harvestable size. You take those out, and then you move everything down one section, and then you would put in a new styrofoam raft and plant new seedlings into that. So the rafts are racing through those channels, so to speak. And this can be really efficient for labor and production in the greenhouse. Some of the advantages, you can have really high planting densities in rafts because you don't use aisles. This leads to high space utilization. And if designed properly, using that example that I just provided, you can get some major labor savings. Now, Another big benefit is the water volume is going to be fairly deep, and it can vary based on the systems, but anywhere from 6 to maybe 10 or 12 inches. I have seen some deeper than that. So pumps breaking down is much less of an issue. I can't tell you how many times I've woke up early in the morning or in the middle of the night wondering, oh, I hope those pumps are still going on the NFT. So this is a real benefit, is that if the pumps goes out, you're really not going to have a problem. Now, some of the disadvantages of this system is you have to think about the oxygen level in the water, because over time, oxygen is going to be depleted. Now, you can recirculate solution into a big reservoir and then reintroduce it into the raceway, and by recirculating that, you can introduce some oxygen. Alternatively, you might want to use some air pumps that will aerate the water and increase the oxygen content. Also, you may need to chill the nutrient solution during warm weather periods. You think about that large volume of water, that can really hold a lot of heat. And so during the summertime, that can hold some extra heat, maybe a little bit more than you might want for the crop that you're producing. Now, the other well-suited system for lettuce and herbs is going to be the nutrient film technique, and this is a pretty common system. Here we've got a series of channels, and this is prior to planting, and these channels are set on a slope. Usually that slope should be between 2 and 3% from where that spaghetti tube is delivering the nutrient solution to where that solution is going to be draining for collection and recirculation. That 2 to 3% slope will allow for adequate movement of the solution down across the roots. And what you may notice here is that looking inside of these channels, you can see just some little ridges, so to speak, in there, and that'll help channel the solution down and keep it centered in the trough. Other trough designs will have a slight valley in the middle of the trough, and that helps kind of channel the nutrient solution. So it's going to be staying in the center of the trough and hitting each of your root zones. Now, just like you have different densities with the deep flow technique, you can also have different densities for different phases of production in the nutrient film technique. So here we've got just a cartoon example, and that top channel is called a nursery channel. And when you look at that, you can see that it's a much higher density of holes in the channel. So this is useful for after germinating your seeds, you can set your plants out into those nursery channels to grow them, and then once they're of transplantable size, move them into your finishing channels. So you can plant high densities to save on space until you're ready to transplant your crops and put them on a final spacing. So some of the advantages of the nutrient film technique, nutrient solution generally has a higher oxygen content because it's constantly moving. So that movement is incorporating oxygen into that water, and you're keeping somewhere around anywhere between 6 and 8 parts per million of oxygen in the solution. Now, another big benefit is that the troughs can be picked up, and this makes harvesting easy. Just like you can pick up those rafts in the deep flow technique, you can also just pick up those nutrient channels. What you do is you take the spaghetti tube out, and then you pinch it off with a little clip to stop water from flowing, and then you can take that channel back to your harvesting and packaging area. Another, I think, opportunity that has yet to be explored too much is that there's a possibility to stack troughs in more than one layer. You haven't seen a lot of this yet, but I think that it is going to be coming sooner or later. Now, some of the disadvantages, and I'd say it's the number one problem with NFT system, is a loss of nutrient solution being delivered to the crop. And this goes back to those spaghetti tubes delivering the solution into the channel. This can happen because of clogged emitters, or if your pump goes out and is not functioning, because we have to have an active pumping of water to that header and delivery from the header to the channel in order to deliver the nutrient solution to the crop. Now, we've got our systems, we've got our seedlings, we're inside the greenhouse. What temperature do we want to set our greenhouse at? Well, it depends. That's kind of a classic answer, but it really does depend. And we'll talk a little bit about some recommended temperatures. But we want to manage air temperature because air temperature controls the rate of growth and development. And managing your air temperature, it's going to have a strong impact on the productivity of your crops. Under cooler temperatures, you don't get leaf unfolding as fast as you would at a warmer temperature. And what are we selling with our leaves? What are we selling with our lettuce and our herbs? Well, we're selling those leaves. And so we need to have those leaves unfolding to produce the yield that we're going to harvest. But different crops have different temperature requirements. Here's just a generic curve, and this shows the impact of average daily temperature, the average over a 24-hour period, on the rate of plant development. And what you'll see here is on the left-hand side, we've got a cool temperature around 50 degrees. And as you increase from 50 degrees, we've got an increase in the rate of development. And this could be the leaf unfolding rate per day. This could be the leaf expansion per day. It could be really any process. This is just a generic biological curve. And it increases until you reach this peak, after which point it starts to decrease. Well, the temperature at which development is maximum, that's called the optimal temperature, when the growth is optimized. And really, the good thing is, in greenhouse crop production, we're generally opting within that range from the cool end to that optimal temperature, and that's called the linear range. So within that linear range, as temperature increases, a process will increase. Whereas when temperatures decrease, the process will decrease. So you can use temperature to control the development of your crop. So here's just an example looking at sweet basil. Again, the #1 culinary herb that's grown today. Now, what do you see here? We've got from 52 degrees up to 95 degrees. And thankfully, this shows pretty well that response I was just talking about. From 52 degrees until 84 degrees, you can see that the rate of growth is increasing. And if you were to look on each individual plant, you can see that there are more leaves that are unfolded as the temperature gets warmer. However, at that 95 degrees, we actually have fewer leaves. So 95 degrees is supra-optimal. So you can tell between 52 and 84 that growth is basically linear and related to temperature. Now also, when you're looking at this, where do we see the maximum growth? Again, that's going to be at 84. So that optimal temperature for basil is going to be around 84 degrees. Now, unless we've got some of you Floridians in the house, and I think there are a couple here, a lot of us aren't going to be growing at 84 degrees. I surely wouldn't want to have that heating bill. But this indicates that sweet basil is going to be a warmer growing crop. Alternatively, let's take a look at flatleaf parsley. Now, it shows a similar trend, but there are some differences. You see between 52 degrees, the growth starts to increase until just about 73 degrees. Now, once we get up into 85 and 95, the growth starts to decrease. So here we have a lower optimal temperature. And this would make sense because we know that parsley is a cooler growing crop. We can also see that looking at the plant grown under 52 degrees, it grows well under cooler temperatures. So flatleaf parsley is going to have a little bit cooler range of temperatures to optimize production than perhaps your sweet basil would. So generally, lettuce is considered a cooler growing crop, but air temperatures that are too cool can delay maturity. And if we run cooler, of course, we're going to save on heat, but it's going to take you longer to get that sizable head of lettuce. For hydroponic lettuce production, 63 to 68 degrees Fahrenheit is generally a fairly reasonable temperature to use during production. Now, there's a little bit more of a challenge when it comes to herbs. The variation in herbs, as you could see by those last two slides, there's a lot more variation among the different species of herbs just because there are a lot more species. With lettuce, it's all the same species, it's just bred slightly differently. Whereas with herbs, we have a lot of different species, totally unrelated genera. So here I've kind of compiled a graph that shows the relative ranges of the air temperature ranges for different herb species, okay? So when you have multiple crops growing in your greenhouse, but you've only got one air temperature, really the best thing you can do is try and select the temperature that is going to do the greatest good for the greatest number of plants in your greenhouse, or the greatest good for that one crop that takes up the greatest area in your greenhouse. So basil being the #1 crop grown and sold hydroponically, that may dictate that you run a little warmer air temperature to favor your basil production. So you just have to kind of balance what you're going to be growing, and that'll help dictate what air temperatures you select. Now, we also want to think about light in the growth and development of our crops. Light has a large impact on the growth of hydroponic lettuce and herbs because light stimulates photosynthesis. Photosynthesis will produce carbohydrates. New carbohydrates stimulate new cells. New cells mean more mass. More growth equals more mass equals more money. And that's what we're interested in, is maximizing the yield of our crops. However, light can become a limiting factor, not during the production season, but in the winter production season. So here we've got some maps of the daily light integral that were constructed at Clemson University. Okay, and what you'll notice here is from October through March, this is the changing DLI across the continental United States. And that deep magenta color is the low light, whereas if you get to the yellows, the greens, the yellows, and the oranges, that's going to be the higher light. And as you look across most of the United States, you can see that from October until December and January, the light levels are low. Somewhere, depending on where you are, anywhere from 5 to about 20 moles outside. However, inside of a greenhouse, light levels can be up to half of the outside DLI because of structure, causing shading, transmission through the glazing material. So we can get some really low light levels in the greenhouse. Well, what happens when you get lower light? So here's an example, again, using sweet basil. We grew these in our greenhouse, same cultivar, new far as the cultivar, grown under low light, around 5 moles per day, or under high light, around 12 to 15 moles per day. And at the bottom, look at the difference in mass, 0.6 ounces versus 1 ounce for that single shoot, and that's the fresh mass. And we take the fresh mass because, again, that's what we're marketing and harvesting. Another example using purple basil. We've got plants grown under the lower DLI on top and plants grown under a higher DLI on the bottom. And for one, you can see that there's a difference in the size of the plants. You know, we've got larger leaves, they're taller plants, probably have an extra leaf or two unfolded, but look at the coloration of that basil, the purple basil, grown under the low light. It's a little bit green. Under low light, you don't get as good anthocyanin production. So it might be a little bit harder to market green purple basil. So the use of supplemental electric light can really help boost productivity of your lettuce and herbs. Now there are several types of lights that may be used to increase light inside of a greenhouse. Probably the most popular is going to be a high pressure sodium lamp. Still widely used for good reasons, but we do have emerging technologies. Hopefully you were all at Roberto Lopez's seminar last week and caught some of the new LED technology coming out. In addition to light and temperature, carbon dioxide can be depleted in the greenhouse. With a closed greenhouse and no venting, we're not getting CO2 in. So we can add CO2 into the greenhouse with one of two ways, a CO2 burner or liquid CO2 injection. And here we have a CO2 burner installed in the greenhouse that can help increase the CO2 concentrations and help improve photosynthesis, again, increasing the growth of our plants. Here's an example. This image was courtesy of Jonathan France. We've got some lettuce that was grown in a greenhouse with no supplemental CO2, and this was in the winter, so it was getting limited. Alternatively, we've got lettuce that was grown on the right in a greenhouse that had supplemental CO2 to maintain a concentration around 500 parts per million. Again, you see more growth, more yield. Now, we've got our environment down, but let's get down to fertilizing our crops. Now, hydroponically grown crops require the same macro and micronutrients that containerized crops require. There's no difference. It's the same plant, just growing in a different system. In a hydroponic system, we're generally measuring the abundance of mineral nutrients much like we would like in a pour-through when we're using electrical conductivity, or EC. But we can also use parts per million as a way to discuss the relative abundance of mineral nutrients. And in hydroponic production, we want to select a target concentration as measured by EC or ppm, and we maintain that by adding stock solution. And depending on the size and the scale of your system, you can either add it manually or you can use peristaltic pumps and it's injected automatically. So this is just an example. Here we've got sweet basil. Again, on the top row, we've got plants that were grown under a low daily light integral, and on the bottom row, plants that were grown under high daily light integral. But we had a range of ECs from 0.5 to 4.0. And really, what can you take away from this? Well, basically, when you start looking at those high ECs, 3 and 4, we're not really seeing much of an increase in growth, regardless of the light level. So you want to try and reduce the amount of fertilizer you have to apply to save on some of your costs, but you want to make sure that you're applying enough to maintain an adequate tissue nutrient concentration in healthy plants. So somewhere between 1 and 2, generally works real well for sweet basil. Now, when you're adding fertilizers, there's going to be 3 primary types of fertilizers. One is going to be a single bag mix, where all the nutrients are in one bag. The second type is going to be a 2-bag mix. This is commonly known as your A and B bag or your A and B tanks. And the third is individual element or individual compound mixes. So single bag mixes, they provide everything you need in one bag. And these can be very easy to use, and that's one of the big benefits of using single bag mixes. Just pick the desired concentration and measure out the required amount of fertilizer to mix your initial solution, and then put together a stock solution to top up the electrical conductivity as it drops as plants use it. However, the ratio of elements to one another is fixed. Since it's all in one bag, you cannot separate the nitrogen from the potassium from the calcium. So it's going to be in that fixed ratio. Now next we've got the 2-bag mix, and this is another popular option for hydroponic fertilizers. The reason we have 2 tanks or 2 bags is that we make concentrated stock solutions that can be used, but they can be made without elements reacting and precipitating out of solution. When elements precipitate, they become out of solution and unavailable to the plants for uptake. So in our A tank, we've got calcium and iron. And in our B tank, we've got phosphates and sulfates. And by keeping them separate at a concentrated strength, we do not get any precipitation of those fertilizers. So here's a shot we've got in our A and B bags up in the top left, and then we've got our A and B tanks after they've been mixed and in the greenhouse. And again, they check the EC in this facility, and if it's low, they add equal volumes of those 2 concentrations to their nutrient reservoir. Instead of doing it by hand, it can be done automated. And so here we've got 3 tanks. One is actually for pH control, so it's a pH controller. But then we've got our A tank for stock fertilizer and our B tank for stock fertilizer. And as the meters measure the EC of this solution, they will continually inject or dose out the appropriate amount to bring the EC up to the appropriate or the target level for your system. Now, the third type, the individual compound fertilizers, these can be used to mix your own fertilizers, and these provide the ultimate control because you can generally add 1 or 2 elements as needed to your desired concentration. However, this can be very time-consuming and tedious, so it may not be for all growers. Just to give you an idea, if you're thinking, well, what should I feed my crops? Well, there are a number of different solutions, but here's just a recommended lettuce solution. You can see nitrogen, 100 to 200 parts per million, phosphorus, 15 to 90 ppms, potassium, 8 to 350. So there are some ranges. So these would be some guidelines if you wanted to try and mix your own fertilizers using individual compounds. And just like we had a challenge with trying to pick an air temperature, what's the EC of your solution? Well, again, we have so much variation in crops, and again, especially among herbs. So you can see, again, this range in nutrient electrical conductivities. What are you going to select? Because generally in a greenhouse, you have usually 1 reservoir, maybe a second or a third, if that. But these are all on a common line. So again, I'd suggest trying to find an EC that does the greatest good for the greatest area of your crops. Okay, so we're talking a lot about fertility, but we have to figure out how we're going to deliver that. And really, we're going to have to put it in some high-quality water. So with that, I'd like to switch it over to Brian Krug, and he is going to take you through the rest of the presentation.
All right, Chris, thank you very much. I'm just getting this thing set away here. All right, so water quality. Chris has alluded to everything that's going to go into the water, but we're going to back up just a little bit and look at the water before we put the fertilizer in. When we're thinking about water quality, there's a number of things that we need to be paying attention to. The electrical conductivity or EC, alkalinity, pH, the water hardness, and then toxicities. So we need to get water tests to determine what all these things are going on with our water. Oftentimes, the growers ask me, how often do I need to test or when do I need to test? And it's not a clear-cut answer always, but my general recommendation is if you are a seasonal greenhouse just growing 1 season out of the year, test your water 1 time at the beginning of that season. If you're going to only grow lettuce and herbs through the winter, about a month or so before you start production, get your water test done. If you're growing crops all year round in your greenhouse, then I recommend doing it twice. Once in the dry season in the summer, and then once in the wet season, the winter or the spring. because water availability in a well or for municipalities can change the water quality from season to season. And usually water tests cost like $30, maybe $40 to do a typical water test with a commercial lab. So it's not really breaking the bank. And when you can see what's going on and use the information from the water tests, you can probably avoid a lot of problems that you might run into. So let's take a look at a water test so you guys get an idea of what we're looking at. A typical water test is going to look something like this when you get the results back. It's going to tell you the soluble salts that's in the water, your pH, your alkalinity, and then all the nutrients that are in the water as well. And different labs kind of report these in a little bit of a different format, but usually they tell you if it's inside or outside of the range that you would normally see. And this is very important to send a test like this. If you're unclear of how to read these water tests, to send it to a horticultural lab and let them know that you're doing production in hydroponics, because that normal range might change from one crop to another or one instance to another. So let's talk about electrical conductivity first. It is the measure of soluble salts that are dissolved in the water. Usually it's in the unit of millimos or millisiemens per centimeter. These are just an electrical unit. The electrical conductivity is what it's doing is it's measuring how much electricity is being conducted through the water from one electrode to another. And those electrodes are usually a centimeter apart, and it gives you an electrical current reading between those two. Pure water conducts very little or no electricity. It's the solutes or the soluble salts that are dissolved in the water that are actually conducting the electricity. So the higher the electrical conductivity, the more salts that are in the water. For our water source, we want our electrical conductivity to be somewhere between 0.3 and 1.0 millisiemens per centimeter. If it's lower than that, it's probably not that big of a deal. If we're starting to get higher than that, then we need to figure out why we're having a higher electrical conductivity and deal with that one way or another. It doesn't necessarily mean that you can't use that water. You just need to know what is in there that's causing the higher electrical conductivity, and then how you're going to deal with it. If you have too high of soluble salts in your water, you can run into wilting, root tip dieback, and leaf necrosis. And what's going on here is that the osmotic pressure or the amount of salt can suck moisture out of the plant, out of the roots, out of the leaves. And that's causing the wilting and the dieback and the necrosis. Now, you may have heard other seminars or read that growers use elevated ECs to create a higher quality crop, and that's true. Some species can tolerate the higher EC levels, and we sometimes increase that. But it's usually something that we have to do over time. It's not something that we can just flip a switch and have high ECs. It's something that plants can tolerate and get accustomed to over time. So one of my favorite topics is about pH and EC. And the question I always get are they the same thing or are they different? And they are in fact different. Let's go over that a little bit. pH, when we're talking about pH, we're talking about the scientific definition is the measure of hydrogen ions in a solution. Actually the log of the hydrogen ions in the solution. So if we have a pH between 0 to 7, we typically consider that acidic. If we have a pH of 7 to 14, we consider that basic, or sometimes considered alkaline. And this is where people get confused about alkalinity and pH. The term alkaline refers to the basicity of the solution or the substrate, not whether it's alkalinity. It's very unfortunate that the root words are very similar, but they are very, very different. Now the pH affects the nutrient availability in the soil solution. So a lot of us are very accustomed to using pH to look at the substrate pH, and is that going to affect our uptake of our elements? In a hydroponic solution, it does affect availability, but it's less so. We still probably want to have a balanced pH. We don't want to have an extreme on one side or the other, but we won't see the extreme effect on pH that we do in the substrate. Now let's talk about alkalinity. What is alkalinity? The definition of alkalinity is the buffering capacity of water to resist change in pH. So usually it's we refer to alkalinity in either carbonate or bicarbonates. And really it's kind of like liming lime that's in our water. Or we use the Tums or other antacids to counteract the acids in our stomachs, and that's a lot of what the alkalinity in water is doing in our growing systems. Is that it's essentially a lime charge. It's using calcium carbonate as a lime to alter to neutralize any acidity. So we measure this in milliequivalents per liter or parts per million, and it's very important to know which unit you're using because they are not equal. They can be easily converted back and forth. Some labs always report in milliequivalents per liter. Other labs report in parts per million. If you get a result back that says that you have 100 parts per million of alkalinity, you might get really excited about that if you're used to getting units in milliequivalents, because in milliequivalents that's the same as about 1.5, 1.25 milliequivalents per liter. So if you're expecting a very low number because you're used to working in milliequivalents, you don't pay attention to the unit that a lab sends you, and it's in parts per million, you might react in an inappropriate way. So to convert them back and forth, you either multiply by 50 or 61, multiply or divide to go back and forth, and it really depends on just how the lab is reporting the alkalinity. So just this graphic here to show you about that resisting change to the pH. So in the top here we have our pH range from 0 to 14, and for most plants, we want to, somewhere in the 6 range where our smiley face is. If we have a low alkalinity in our water, if we apply some sort of a force or introduce some type of an acid, the pH, because of the low alkalinity, is going to shift very fast. Now, if we apply the same pressure on a system that has high alkalinity in it, it's going to move very slow, and it's not going to move very far. So hopefully that it's a little bit of an abstract topic with alkalinity, and it's no surprise that it's hard for people, myself included, to get this wrapped around our heads. But alkalinity and pH is very different. Alkalinity usually influences pH. Now, if we look at a couple of different water samples looking at alkalinity versus pH, in water sample A, we have a pH of 7.5 and an alkalinity of 1.5. And in water sample B, the pH is 7.5 and it has an alkalinity of 7 milliequivalents per liter. Now, a lot of growers, when I ask what their water quality is like, they'll say, like, oh, it's fine. I have a pH of about 6. Or they'll say, like, well, I have a problem with my water. My pH is 7.5, 8.0, and they get concerned about it. And really, pH in our water quality is not overly concerning, depending on what our alkalinity is. Water sample A is acceptable because we have a very low alkalinity. We can change that pH very easily, and it's not going to affect our water that our plants are being exposed to. Now, if we have a pH of 7.5 and we have a high alkalinity, like a 7 milliequivalents per liter, then it becomes problematic because managing that alkalinity becomes more difficult, and we have to think about what we're going to do with it. It's not impossible to overcome, especially those of you that live in the Midwest. You're probably looking at this and very familiar with a water sample that looks like that. So we can deal with it. We just need to know what we're working with. Again, let's look at this just to give you an idea of how these different water sample sources are going to work. Now, this is in pot culture, just to give you the idea. It might work a little bit different in a hydroponic system. But water sample A, if we have a pH of 7.5 and an alkalinity of 1.5, and we're irrigating our pots over time, we will see that our pH will increase over time. But notice it went from a 5.8 to a 6.2 over time, and this could be over a matter of weeks. And it really didn't change that much. Now, if we use water sample B with an alkalinity of 7 milliequivalents per liter, over the same amount of time, we're going to go from a 5.8 to a 7.4. So essentially, every time that we irrigate these plants, we're adding some lime, like a lime effect to it. Here's where we start to deal with what to do with our alkalinity. If we have an alkalinity of 2.0 milliequivalents or lower, or about 120 parts per million, we probably don't have to do much at all. If we have an alkalinity of between 2 and 3, then we need to start thinking about using an acid fertilizer or using less lime in pot culture, not so much in hydroponics. Somewhere between a 3.0 to 8.0, which is very similar to rates that we see in the Midwest, we have to start using acid injection. Above that, we start getting into reverse osmosis, and it gets very expensive. When we're using acid injection to correct our alkalinity, some acids of choice are usually nitric acid, phosphoric acid, or sulfuric acid. Sulfuric acid is usually our prime one that we use for a number of reasons. It's usually cheaper, and if we use phosphoric or nitric acid, we need to worry about how much phosphorus or nitrogen those acids are applying to our irrigation water and subtract that out of our fertilizer regime. Sulfuric acid, it will add sulfur, but you'll be hard-pressed to find a sulfur toxicity in your plants. So we don't really have to worry about changing our fertilizer rates. Like I just mentioned, adding the acid neutralizes the alkalinity in the water and drops that alkalinity out of the source water. Nutrients are added when you use these three acids, so be aware of that, especially if you're using the nitric or the phosphoric acid. As I mentioned, sulfuric acid is our preferred acid because we usually don't have to worry about it. If you're trying to figure out how much acid to inject, we have come up with a program called AlkCalc. It was first developed by Alan Hammer at Purdue University, and Brian Whipker and myself, we have updated it and made it a little bit more accessible in a web form, and you can go to that on nhfloriculture.com. Hardness, again, not something that we deal with too much on the East Coast, but on the Midwest, a little bit more of a problem, and it's usually the combined content of calcium and magnesium. We talk about it in milliequivalents or parts per million, and it's really the ratio of calcium to magnesium. What we're looking for is a ratio between 3 and 5 to 1. So, 3 parts of calcium for 1 part of magnesium. And the reason we're looking for this ratio is if we have too much calcium in relation to magnesium or vice versa, these two elements compete with each other for being taken up by the plant. So if we have an imbalance here, we can run into some nutrient deficiencies in calcium or magnesium. So here we have just another water test, and we look at the calcium and magnesium output of this test, and we notice that it has a ratio of 1 to 11. Now, that is going to cause excess calcium. This excess calcium will block magnesium uptake because we're out of sync with our ratio, which we were looking for that 3 to 5 to 1, and we'll probably run into magnesium deficiency. Conversely, in this test, we have a 2 to 1 calcium to magnesium ratio, and this is going to have the excess magnesium, and it's going to block calcium uptake, and we'll probably start running into calcium deficiencies. Finally, with this test, we have a calcium magnesium ratio of 4 to 1, and this is going to be a properly balanced water, and we're not going to run into problems with calcium or magnesium competing with each other. Now, if we do have a calcium magnesium hardness problem in our water, we can correct it by using a different fertilizer mix that is a little bit heavier in one or to the other to get that final solution that the plants are experiencing to this 4 to 1, 5 to 1 ratio. Some other notable elements that I want to bring up. I'm not going to go through every different element, but sodium. The critical limit for sodium is about 50 parts per million. And I bring this up because over time, especially in something like a deep flow system or an NFT system that you're not replenishing water very often, the sodium increases over time because the sodium is getting concentrated as the plants use the water and the other elements. They're not taking up sodium as much as the critical elements, the essential elements, so the sodium gets left behind and it builds up over time. If we have too high sodium levels, it can start to inhibit uptake of potassium, ammonium, calcium, and magnesium. So we want to, even though sodium isn't an essential element for plants, we need to be monitoring this so it doesn't throw the rest of our fertilizer program out of whack. Chlorine. We can easily get confused with chloride. It's just a different form of the same element. If we have chlorine, it's bad. Chloride, we can deal with. The critical limit for chlorine is 0.4 parts per million. It can cause root tip burn. The chlorine reacts with organic matter to convert it into chloride, but hopefully we don't have a whole lot of organic matter in our solution, because it might clog up our pumps and whatnot. So we need to deal with it somehow. Usually aerating the water or using a carbon filter will usually remove most of the chlorine. So again, not hard to deal with, but we do need to do our water test to make sure we don't have too much chlorine in our water. And if we do, we just need to take appropriate actions. The critical limit for iron is 4 parts per million. And when we're talking about iron in our water, we can start to get some iron bacteria growth in our water if we have as little as 0.5 parts per million. And this bacteria can plug up our equipment if we're doing an NFT system and we have the spaghetti tubes, or we just have a water pump. It can start to cause problems by clogging all that stuff up. And especially in an NFT system, if something gets clogged up, the crop is going to show you very quickly, and you have a very limited time to get this fixed. Fluoride, it's added to a lot of municipal water. So if you're in a city and using municipal water, you need to be watching for this. The critical limit, or in municipalities, can put anywhere to 0.5 to 1 parts per million of fluoride in the water, and the critical limit for a lot of plants is 0.5 parts per million. Not a hydroponic crop here that I'm showing, but a lot of times we see this with lilies and other foliage crops. They're very sensitive to fluoride, so again, just something to be aware of. Just some other critical limits for other elements. Nothing to be overly concerned with, but manganese, zinc, copper, and boron, here are the critical limits for that. They're in your handout. Don't have anything really notable to mention about them, but again, just paying attention to what's there and maybe having to alter your fertilizer program accordingly. So the magnesium and zinc and copper, this is safe for irrigation water, and probably even higher than this you can get away with. These three don't cause a lot of problems. Boron, if you get much over a part per million in your irrigation water, you can start seeing some toxicity problems. So we've gone through a lot of things with water quality. So hopefully now you know the answers to what all these terms of water quality means and how you need to manage them for your crops. There's a few other considerations that I want to go over. I'll go over these really quickly, getting away from the growing and into the marketing of your crop, because we can grow it all we want, but if we can't sell it, we're not making any money. One thing that's been really popular here in New England is the winter's farmers markets, and this is such a key place to be selling our hydroponic crops that we can grow in the greenhouse. Some considerations of why or why not to grow in the winter. It's a growing, it can be very different growing crops in the winter than what we're used to growing bedding plants or poinsettias in the greenhouse. We have to have some special considerations. If we're moving these plants around from one greenhouse to another, if you have a propagation house and then a production house, or you're just trying to harvest and getting them out of the greenhouse, you have snow to deal with. Scheduling and crop management can be different because Chris talked a lot about light, and if you're not using supplemental light, you have to really figure out how this cycle of cropping is going to go, because as we get less and less light, production is going to slow down, and how do we stagger these successive crops so that we have product on a regular basis. Harvesting can be an issue. We're used to, and for greenhouse growers, we're used to just pulling the pot off the bench, and we don't have to worry about too much. But this is a perishable crop, much more than our bedding plants. We need to have some things in mind when we're harvesting. Growing hydroponic lettuce and herbs is nice because you can get the year-round income that you might not have because of those gap periods that Chris talked about. To really round that out, you're gaining value from that vacant space in your greenhouse. We all know that greenhouse space costs us some amount of money on a square foot basis, whether it's in production or not. So getting some profit out of that empty space is really nice. But it can be challenging. Like I mentioned, planting these winter crops can be hard because you really have to be thinking about this in July, August, and September of when you're going to have these successive plantings or sowings so that you can have a consistent crop all the way through the winter. Dealing with the harvest of logistics in the snow and cold, I mentioned that a little bit. And a lot of growers really value this downtime in the winter, and you are giving that up. You're giving it up for higher profits potentially, but it's something to consider that you're not going to have those couple of months to clean out your greenhouse, to have a little bit of a slower pace to your year. Food safety is something that we haven't had to think about a lot in greenhouse production. So we need to the first thing that comes to mind is we needed to rethink our pest management methods. We have a very large arsenal of things that we can use to control our pests for bedding plants and flowers. But many of those products are not registered for edibles. And this is a fundamental difference from transplants. There's things that we can use on tomato transplants that we can't use on tomato that are producing fruit in the greenhouse, and same with transplants of other vegetables and herbs. Because of the application time is so close, the application time of some of these pesticides are so close to when they're harvested and consumed, there's a very big fundamental difference in using these pesticides in an edible crop. Many of you may or may not have heard of FSMA, or the Food Safety and Modernization Act. It was passed in 2011. I am not by any means an expert in this. I know just enough to be dangerous. I just want to make you guys aware of it so that you know that you do have to pay attention to this. The rules and regulations are in draft form, and they go into effect this fall. We should have 1 to 6 years to come into compliance with this, so it's not like necessarily just turning on a switch and wake up one day and everything is different. But it's really looking at food-based illnesses. You are liable for some food-borne illnesses, so you need to have liability insurance if you're going to be growing edible crops. Talk to your local extension and regulation folks. They are going to know. They are going to be the experts in this, not Chris or I. Again, we just want to make you guys aware of this stuff. Keeping good records of your sales are very important when it comes to this law. You may not be covered by FSMA or have to live by its rules if you have less than $25,000 in sales from edible produce. Now this goes up to $500,000 if half of it is marketed direct. So if you're selling it directly to the consumer and not as a wholesale market, you have a little bit more leeway as well. Post-harvest, you need to think about cleaning. If there's anything that needs to be cleaned off of this, it's something that we're not used to be doing with flowers and bedding plants. We're used to dealing with perishable products, but most of the time our products still have the roots and are still living. When you cut these crops, they are in the process of dying. So you have to get them to market immediately, and you need to have some type of cold storage for many of these crops. And some of them might have different cold storage needs and be able to tolerate different cold temperatures for storage. When you're marketing your product, a lot of people are using direct sales, either through their garden center or a farm stand, or going to a farmer's market. I've heard a lot of people focusing on restaurants as well. All of these have pros and cons. I'm running out of time, so I don't want to go into all of this in detail. And then grocery stores as well. When you're thinking about what to grow, especially when it comes to greens, there's a variety of different things that you can sell, and you may not want to have just one thing because you want to have what your consumers want and to have a good mix. If you look at the different things, you can look at your lettuces and your spinaches for creating bulk, your chards and your beets for creating color in your mix. You want to think about shape. What are the different green shapes? What are the leaf shapes so that you have some aesthetics to it? And then flavor, you can add in a few mustards and to get some spice, especially if you're going to create a salad mix. It can be a really nice way to round out your product, to look at this, to maximize your value for your customer, and also the value for you of which is going to grow fast and create bulk, and what do you need a little bit less of to create spice. We haven't talked about it a lot, but usually we're going to be probably, unless we're doing like the butterhead lettuce, we're looking at probably baby salad greens, and probably anywhere from 6 to 10 centimeters is what we can consider a baby salad green. So that was a very whirlwind hour here, but that is growing greens and herbs hydroponically in a nutshell. With that, I want to thank our sponsor, Hort Americas, for bringing this webinar to us and making it free for all of you. I'm just unmuting Chris Curry here. We do have some time for some questions. If anybody wants to type in some questions in the chat window of your go-to training control panel, Chris and I will answer some of those. Chris, it looks like you have kind of paid attention to some of the questions that have come in. Are there any that need to be answered?
I think I've answered them as they've come, so I can go over those answers, or we can ask some different new questions. I'm whatever's clever.
All right. Well, let's give them a minute or two to see if any new questions come in. I know there was a quick question about the how deep the deep flow needs to be. I'm sure that you already answered that, Chris.
Yeah, yep, 6 to 12 inches. Although really, it kind of depends. It can be 4 inches. It could be 2 feet. But just the general range. That's just a general range. There's a question here. Let me get back up to it from Kurt Taylor. Are there any crop budgets for different hydro crops? Um, I have not seen many that are. I don't know that I can recall seeing any, and it comes down to one of those situations of which crop are you growing? What size is your greenhouse? What's your glazing material? There, there gets to be a lot of variables. So putting together a generic budget can be kind of challenging. How often do you switch out your water? What's your water source? So unfortunately, I'm not sure that I've seen that, and it would be pretty challenging to put together. Probably not the answer you're looking for.
There was a question about is the audio of this webinar going to be available? Yes, we are recording this. Give us about a week or two to get it formatted and everything, and we will get that posted on our website, e-GRO.org.
I've got a question from Lindsay. What's the easiest way to grow baby leaf greens in a hydro system? Well, Lindsay, it would not be the systems that we talked about today. I know Brian has done work with growing young greens in a substrate-based system, but the best way to grow baby greens is going to be growing them on some sort of, I've seen burlap mats used. You can get, otherwise you can get some, I forget the name. It feels like cotton batting almost, but you kind of roll that out and sow your seeds into there and then grow them on that and then just trim them off. So it would be a different system than today. So yeah, you're right. Having baby greens and plugs, it'd be time consuming to harvest. It would take up too much space. So it would be an entirely different system than this one.
There's a question about can the water be heated to provide much of the warmth needed for these crops? Chris, please interject if you disagree, but in a deep flow, maybe, but oftentimes the floating device that the crops are on oftentimes are styrofoam or some type of an insulation, so you wouldn't get a lot of heat transfer up into the air, and you can the plants have a limit to what they can tolerate for warm water, and then also the volume of the water that you have might not actually be enough to really have much of an impact on the air temperature or the growing temperature. I have seen where you had to heat the water, especially in an NFT system, a certain amount, because if you have a cool air temperature and you have such a small volume of water trickling through those growing gutters, the water cools off as it's traveling through the gutter, especially if you have a longer gutter system. So that's not really what you're asking, Beth, but that can be an issue that you do have to heat it depending on how warm you're running your greenhouse. Chris, do you have anything to add on that?
Yeah, I can speak to it a little bit. I think Brian addressed NFT really well. It would be really difficult to provide with the small volume of water in that trough. It would be difficult for that NFT solution to provide too much energy to that plant. And I think this is kind of what you're saying, like with bottom heating, you can sometimes use lower air temperatures. Or if you're growing on a cement floor with floor heating, you can kind of reduce your air temperatures. However, there is some possibility that you could do a little bit of that with the deep flow, because I know just in my experience here, we've had some of our deep flow tanks or our deep flow systems right on the floor, and we have in-floor heating, and then we had the exact same NFT system set up right next to it, and crops in the deep flow definitely grew more quickly. They developed more. They developed more quickly. If you kind of think back to that curve that I had with temperature, they were of marketable size earlier because they were getting that radiant energy or they were getting that energy from the floor, and that was in turn heating the plant. So there's a larger volume of water. It can hold more heat. As far as looking at reducing your air temperature, I don't know how much, to what degree you'd be able to reduce your air temperature if you're using that the deep flow technique. A couple of degrees perhaps, but if you're talking more than 10, that might be difficult to make that heat up, because you think about it, you do have that piece of styrofoam that's kind of buffering the transfer of heat up to the plant. So you can maybe buy a couple of degrees, and this is just speculation. I should be forthcoming with that. You might be able to reduce your air temperature a couple of degrees if you're using deep flow and heating the water as opposed to NFT. But a bigger difference than that, it might be difficult.
All right. Just had a question about, can different plant species grow on the same nutrient solution? Or do they need different nutrient solutions for each of the plant species that we grow?
Do you want to take that? Do you want me to take that?
I'll give it a shot, and you can disagree or agree with me. I think it's very similar to what Chris was showing with the temperatures. You have to find something that's manageable. It's probably not realistic to have a whole bunch of different fertilizer solutions for all your different crops. So finding something that's kind of in the middle, or erring on the crop that's taking up the most amount of space or is the most profitable for you. I have grown a number of different species in the same system, and it seemed to do okay. I'm not sure I had any of them optimized. Like, we were just growing them to get our systems up and running, so we weren't taking any yield data on it, but most people would say that they looked okay. Chris, what do you have to say about that?
Brian, you handled it excellently.
That's what I like to hear.
It's kind of it's a great quote from Gifford Pinchot, the guy who started the U.S. Forest Service. He's John Muir's counterpart. Wonderful person. Get into history and check him out. But the greatest good for the greatest number. And so when you look across your greenhouse with all the different species, you kind of have to pick the one that's going to do the least damage to the majority of the crops. So I know one of our herb growers, he's got probably 20, 25 different species, and it all runs off of one EC, and some stuff could be grown a little bit better, I'm sure, if he raised or lowered it, but for the most part, it works out. If you did have the opportunity to have a couple of reservoirs, that might be useful. But yeah, you can just find that balance that works for a majority of your crops.
All right, Jocelyn asked a question about, is there any way to produce crops in hydroponics and have it certified organic?
I have not seen. I'd be curious. Steve Millett, I don't know if he's still on the line, so I'd be curious to hear from Steve, since I know he sees a lot of operations. But I have not seen any, if not many, because when you think about organic nutrients, generally it's not in that raw elemental form. It's in something that's going to get converted for use in the soil, and then the plants take it up. But when you think about hydroponics, we really don't have a lot of fauna in that water, or at least hopefully we don't have a lot of fauna in the water. If Dr. Rodalice in Yukon is on the scene, but you don't have that conversion of nutrients like by microbes. So that's one of the biggest limiting factors. So if you're interested in doing hydroponics, it's a slight change of hydroponics, but if you were growing herbs in a bed of media, then I think there would be a better chance to have a certified organic operation, because you can grow in like peat perlite substrates and get certified organic and use organic nutrients. And so that might be a better way to produce, strictly speaking about culinary herbs, produce organic herbs not in field soils.
Yeah, and I would agree. I haven't really seen any certified organically produced hydroponics. A lot of it is going to come down to your local certifier. There's the organic certification process is doesn't have a lot hard rules when it comes to hydroponic stuff. So if you're using an organic fertilizer, there are some liquid organic fertilizers out there, but there's the issues that Chris talked about. You might find a certifier that would do it, but a lot of people feel very strongly about organic production requiring the presence of soil, and just like building the soil. A lot of organic production philosophies involve the building of the soil over time, and we don't have any soil, so we can't build that over time. So it's kind of a thing that you have to deal with, and my opinion is, having a relationship with your customer is probably as or more important than the organic certification, especially on a small local scale.
There's a question here from Kurt. How effective is it to stagger the crop dates in an NFT system when you have crops of different levels of maturity, from those heads that are getting ready to be harvested to those recently planted lettuce seedlings? It works out just fine. Granted, again, if we could optimize it, I'm sure we could find different optimal levels of nutrition throughout the production phase. But it's no problem, to have an EC of around 1.4, 1.5 maybe for butterhead, and that'll work fine for your seedlings all the way up to your mature plants. So it's no problem at all to have crops at varying stages.
All right. Well, I think we are running out of time. We're over our allotted time. So as I mentioned before, this is recorded. This will be posted on our website. One final time, I want to thank Hort Americas for their sponsorship of this webinar, making it free of charge for all of you, so that we can get this information out. I'd like to thank Chris Curry for joining me on the webinar and helping me out. So I hope you all are getting excited about growing lettuce and herbs in your greenhouse hydroponically.